Do you guys, anyone else? I just need to know how many students got a problem, okay? Yeah, okay. So, okay, okay. Yeah, well, Aramis, if you look at the file, because this is a virtual lab, so if you need help, you need to send email them anytime to make appointment, okay, to see them, okay? And well, yeah, I understand, but you see, but because of the the virtual issue, right? What is that? What do you mean by why isn't that used to show us the lab? Okay, so Aramis, you want the lab hours, and then other times you don't want access to them, right? Is that what you mean? Or you want to access them anytime you want? Okay, Aramis, this is the case because this is a virtual lab. It's not a virtual physical lab. So yeah, I can ask them to show up during the the lab time. That's only 3 hours. But not everyone is gonna go to the virtual lab because we have no control about that. Then if we ask the GA to show up at the during the 3 hours, then for other times they're not obligated to show up. You see what I mean? Because they only got paid for 3 hours lab, right? Okay, so this way, if you need help, you can make appointment with them anytime you want. I think it's more efficient because not everyone is going to show up in the virtual lab, and also we have no control for that. Not like the physical lab. You show up or not show up, we have the control, right? But in this case, because it's a virtual nature, so we have to take advantage of the virtual nature. So that's why I specify that if you need help, you can email them, make appointment them, anytime you want, right? Okay. Well, yeah, that's another issue. It's okay. Well, okay, yeah. You know what? I can tell. Well, that one I can talk to GA to see if there is a better way, to, let's say, virtual meeting or whatever. Okay. Which way do you guys want? You want the GA just show up for 3 hours, and then other time if you make appointment, they might say no. Well, James, it is the first time for everyone to use this software, not just you. Okay. Well, that's another issue, RMS. Okay, because the Faculty of Engineering, they purchased the license virtual lab, of this virtual lab, and this is the first time. Okay, this is the first time because they've just got it installed in fall, so this is the first time for us to use it. Okay, I can understand. There are a lot of there might be some issues, but we'll try to contact them. Contact them to see, if we can get some help. Okay, you can see that anytime when you send an email to me or to the GA, if they can solve it, they reply right away. If they could not solve it, we forward your, your inquiry to our, lab manager, technicians, immediately. Okay. Okay. Well, okay, yeah, okay. Now, okay, this is what I can do. Okay, I can ask them to go to during the lab time to make a demo instruction about because the software. Well, you see, most of the time, most of the students complain about the problem is no, lab technician is not a GA. Okay, Sebastian. Okay, because you see, we basically we are supposed to be backed by the lab technician. Okay, because there's a license. You see, this kind of a license issue, it seems like. Well, seems like I will think about to extend the due date. Okay, so that one is not a problem. Okay. Yeah. So well, but you see, right now, okay. Well, I think that the biggest issue is that should we go for the virtual lab or not? We can switch back to the main lab. Well, you see, Harmanjit, I'm pretty sure, okay, to give you a demo that is very easy because the procedure itself is very easy. However, it does not mean that you follow the same procedure, the problem will not come. Seems like a lot of time I see the back and forth email. I see the solutions provided by our technician, and it seems like a lot of time that the problem is generated not by that you did not follow the procedure. It seems like it's about the user numbers, and I don't know. I mean, to be honest, we were instructed by those procedures, and when we tried, we did not have any problem. You see what I mean? But when you try it, you got a problem. So we don't know what. So okay, if we ask a GA to show you the demo, they can only show you those procedures. But when you when you log in to do your lab, you might get a problem too. Still, get some problem. Now what are we gonna do? You see what I mean? So it's not just follow the procedure or not, because the procedure is clear because I already posted. But apparently, when you follow the procedure, you claim that you got a problem. You still got a problem. You see what I mean? Right? So I think that is the key. It's not actually. If you look at just the procedures, our GAs were already working on this kind of issues before the lecture starts. Okay, the procedures. Okay, and we tested. We did not find any problem. You see what I mean? Okay, but when you try it, so that's why we tell you the procedures. We post it on the on the website, right, on the Blackboard. Okay, and tell you, okay, this is the help. You remember there is a link. Okay, right? I think that's the key. We don't know how many, what kind of issues could happen when multiple students try to use it at the same time. You see what I mean? So that is why I really don't think that everybody should, go there during the lab time and do the same time. So the server, I honestly tell you, I think the server might get crash. but we don't know what exactly happened. Okay, you see what I mean? So that is why I encourage you guys to take advantage of a virtual lab. Okay, because you can access it another time, you know. Okay, so I think that if you guys you never know. Aramis, I wouldn't say that. Okay, you never know. Okay. Okay. Well, you see, the license issues, like what I said. Okay, when we use it, we didn't got this license issue. And later on, you know, our technicians send, you know, some further, you know, instruction. I mean, basically, it's a hint. If you look at those, you know, instructions, they're not just talking about, oh, what kind of procedure. The procedure is the same. Okay, basically the technician did not change the procedure. It's just some small tricks, you know. Oh, you did not close the model, you know, appropriately. Oh, you have to wait for a while. You know, this procedure is just like that. That's exactly what I want to say. That is exactly the problem. You see what I mean? So, if I think that if we continue to have this kind of problem, maybe starting from the second, you know, lab, we're gonna, you know, just switch back to the, you know, the MATLAB. Will that work for you? I mean, apparently the MATLAB, you know, will not be as fancy as this virtual lab. Okay. Okay. Yeah. Okay. Okay. And then I will, you know, yeah. I mean, actually, if we switch back to the MATLAB, then our life is much easier. Our life, okay, okay, you know, but you know, I'm sorry, just fix the problem, right? Yeah, you see, okay, well, it's not that we want to fix the problem, right? But you know, after we post, you know, we got the hint, we got the instruction, you know, from the technician, even from the Quanza guys, you know. But you know, this student still got a problem. Okay, and to be honest, because I'm not beside your, you know, computer. I don't know what kind of procedure you're doing. Even if you post the screenshot, you did not post this procedure that you did. Okay, you see what I mean? So it's not gonna be easy to figure out what exactly your problem is gonna be. Okay, I honestly tell you that. Well, I think that the most important is we have to try, you know, several times to figure out what is the problem. I mean, seems like those you know, instructions, it's like you tested it many times and you got the experience and say, oh, hey, you know, like any other software, right? So if you guys don't want it, I mean, I personally think that if the virtual lab works, it will help you better because it's pretty much imitate the physical lab. But if you don't want and you want to switch back to the MATLAB, and then that's really, you know, just you know, very very what do you mean, Fatima? There is a submission, you know, site. You need to submit to the report. What do you mean? Where can you post? I don't understand your question. When you finish it, why you talk about you know, post? You mean submission, right? Oh, it's probably I have not made it, you know, available to you because the due date is not yet. So yeah, and seems like I have to extend the deadline for the lab one. Okay. Don't worry about the submission. Okay, the submission will be there. That's not an issue. Okay? No, we're going to extend that. Okay? Okay? But the most important is that should we continue or not? It seems like a majority of you don't agree to continue with the virtual lab. Is that right? Okay. Continue. Well, the first lab you still use the virtual lab for the first lab. No, there's no change to the. You should not switch it to the the main lab. You should finish it. I will extend the deadline to give you more time to finish it. Okay. Okay. So if we decide to switch back to the main lab, it's gonna start from the lab 2. To be fair to everybody. You see what I mean? Okay. Okay. So yeah. So I think that we cannot continue. We cannot spend more time on the discussing this. Okay. So okay. Now the decision. I will post an announcement on the lab on the Blackboard. Okay. That might be a good suggestion. So do you want me to give you the option? I think that's a good suggestion. Okay. Yeah. Okay, but it will not be give any credit, for when you choose any one option. Will you agree with that? That should be on your own decision. Tara, don't cry. Okay, you know what? It's always good to it is always good to. Okay, how about like this? Okay, I will give you the option. Okay, either use virtual lab. Seems like you still like the virtual lab. It's just it does not work smoothly. Okay, which we can understand. We have 90 students. I already talked about it. I already asked the technician how many licenses we should have, and actually our technician told me that it's infinite. It's infinity. Okay, it's unlimited. Okay, so but I guess that if everybody, because you see this virtual lab, it's actually installed in Kwanzaa's server, not on our university server. The university is a portal. It's only a portal. Okay. Okay. So anytime when you guys work, you're actually logging into Kwanzaa's server to work on those virtual lab. You see what I mean? So I think that might cause some problem when everybody, when more users, get into it, right? And also, also, you never know how many users, from University of Windsor, it's our class use it. We don't know if at the same time if other university has used it or not. We don't know. Okay, we don't know that. Apparently, Kwanzaa did not, okay. So I think that yeah. Well, Adam, there's not fair or not fair. It's your option. Okay. If you work on the virtual lab, no bonus, definitely no bonus. Okay, it's on your decision to. I give you the chance to have a better experience with the virtual lab. Okay, and you can try it. Okay, but if you cannot make it, and then you come back to at least you have the bottom line. You see what I mean? Okay. Okay, yeah, Brian, that's well said. Okay, all right, okay, so let's stop the discussion. Okay, stop the discussion. Okay, Brian, I agree with you. I agree with Brian too. Okay, okay, let's stop the discussion. Okay, and the decision is going to be like this. Okay, and starting from the first for the lab 1, to be fair, everybody has to finish it, you know, with the virtual lab. Okay, and I will give you the extension of the deadline. Okay, and the second, I will starting from the lab 2, I will give you the option, and you can either use the virtual lab or use the, you know, the MATLAB. Okay, and you will get an equal credit. You see what I mean? Okay, okay, yeah, okay, stop. Okay, now that's it, period. Okay, okay, and also for the assignment 1, because I think that probably a lot of students stuck with the you know, lab 1 for quite a while. Okay, so I will also give you the extension for the assignment 2. Okay, okay, the extension of the deadline for the assignment 2. Okay, okay, yeah, okay. Now stop discussion. Okay, now we need to have the lecture. Okay, okay, so yeah, we're gonna have so in the last class I talked about the relation between the open loop system and the closed loop system performance relation, right? Because that's what we needed, like what I said. That is exactly what we needed. What we needed for the control design, because we want to work on the open loop system, not on the closed loop system, right? I repeatedly emphasize, you really need to get this point, okay? Because when you work on the open loop system's information, it will have a lot of advantages, okay? And any design, if it needs the closed loop, you know, system model, that's not information. That is not a good design method, because you see, before you figure out, you see, this is the conflicting issues, right? You see, like in this picture, here I said that this G of S actually is including both the plant and the controller. How come you have not figured out the controller design? How come you know the G of S? If you don't know the G of S, how do you know the closed loop? You see what I mean? So if you need a closed loop information, then you got to stack it. Okay, which one first? You have the controller first. You have the closed loop, you know, system information first, right? We can only be given the closed loop system performance design, the requirement, right? That one, it's okay. Say you want a closed loop system stability, you want a closed loop, you know, tracking performance, you want a closed loop the transient performance. That are the performance index, performance, you know, criterion that we needed. That is okay, because that's our goal, okay? But the design method should not require the knowledge of the closed loop system's information, the model information. You see what I mean? If you stuck, you know, with the closed loop system model, just like the Rose-Hurwitz criterion, right? You see, let's say I keep mentioning that the Rose-Hurwitz criterion is not like the Nyquist stability criterion. It does need a closed loop system model to allow you to apply it to get the information of the closed loop system stability, right? If you do not have the closed loop system's denominator polynomial, then you cannot apply the Rose-Hurwitz criterion, okay? But before you figure out the control design, you don't have that information. So basically, the Rose-Hurwitz criterion, it's not a good, you know, tool for design. It is a good tool for analysis, but it's not a good tool for design. You see what I mean? Okay, so yeah, we spend a lot of time to talk about you know, the relation between the stability and the between the open loop information, and the closed system stability, right? Which is answered by the relation is answered by the Nyquist stability criteria, right? And also I talk about the tracking performance, right? The tracking performance, which is it's here, okay? It's here, right? So we know that as long as we reconfigure the open loop system model into this kind of NK type, okay? Well, I don't need to say more, okay? I've already said this too many times. You should know that, right? How to reconfigure the model of G of S, into this kind of format, and then you will be able to tell the closed loop system the tracking performance, right? And for the transient, I said that the situation is a little bit more complicated because the performance index defined is multiple. So, and also the performance requirement for the first order and second order system, they are different. So normally for the first order system, it's simpler. We only need one parameter to characterize, okay, which is a time constant, okay. But for the second order system, the situation is not that easy. Okay, then in order to demonstrate the relation, we use a standard second order system as an example to show you what kind of a relation, okay? And actually, specifically, we decompose the standard second order system into an open loop system plus a unity feedback structure, okay? Solely because I want to show what is the relation between the open loop system and the closed loop system transient performance. And for that, we find out that the phase margin of the open loop system, right? The phase margin is read from the open loop system transfer function, right? So we find out that, oh yeah, the phase margin is a very good, performance criteria index, okay? And this can be read from the open loop transfer function, while at the same time, we find out that the relation between the open loop system's phase margin and the closed loop system's damping ratio, okay? The relation is, actually, for a certain kind of a range, the relation is straightforward and simple. And that is something we like it, okay? Because you see, right now, you can see that if you read the open loop system's phase margin, you can predict what is going to be the closed loop system's damping ratio right away, which is very nice. And also, I said that this phase margin actually is the extension, it's a generalization of the damping ratio, okay? We use the second order system to show this relation. And for the second order system case, the phase margin does have a clear and explicit interpretation of the damping ratio. However, because for the high order system, okay, we don't have the, the clear and explicit definition of the damping ratio, right? If we have any system that is above the third order, we actually do not have a very clear, definition. So what exactly is the damping ratio? Okay, but in this case, because we know that the phase margin actually indicates the damping nature, so that's why for the phase margin has another, has another application. It's that for the high order system, I actually forget about the damping. I can use actually straightforward the open loop system phase margin to indicate the damping nature, even if I don't have a clear definition and a clear interpretation. Okay, so from now on, you should treat that the phase margin represents the damping nature of the system, regardless of the order of the system. You see what I mean? So this is a generalization of the damping concept. Okay, so you can see this phase margin is a very good quantity that we figured out. Okay, so that is why the Nyquist stability is very, very popular. Okay, in the control design, in a lot of system, any engineering that needs the related to the system. Okay, so the Nyquist criterion found a lot of applications in this case, okay? Because the phase margin is really a very excellent concept. Okay, now on the other hand, we also developed the phase margins crossover frequency. Okay. See, the phase margin is really important. Actually, both quantity. Okay, the phase margin crossover frequency and the phase margin itself, both of them are useful. Okay, because the phase margin crossover frequency actually has a relation to the closed loop system's bandwidth. Okay, omega b. Okay, it's an indication of that bandwidth, and that bandwidth is very important. It's another important performance requirement for the closed loop system, for our physical system, right? So that's why we can summarize it, the relation in this two quantities case. You see, crossover phase margin crossover frequency and the phase margin itself, and their relation to the closed loop system damping and the bandwidth. And by the way, when we have the bandwidth, we use the bandwidth, we don't need to use the natural frequency anymore. Because you know why? Because the natural frequency and the bandwidth, they're exactly the same. Okay, they're exactly the same. They are indicated in this relation. Okay, in this equation, right? Okay. You see, they're pretty much can be used alternatively. Okay, so that is why we normally only use bandwidth as a performance index, because if you know the requirement for the bandwidth, you know the requirement for the natural frequency. Okay, and then you know what you needed for the phase margin crossover frequency. Okay. And this is how the this what I just said, how we read it from the Bode plot. I don't need to mention this because I've already talked about that one when I talk about the Bode and the Nyquist plot, right? So like what I said, the Nyquist plot has a good interpretation of what happens. Okay, the phase margin, gain margin, you can see it clearly. Okay, and geometrically it is good. Okay, but the problem is that the Nyquist plot is not good for the design, to play with the design issues. It is the Bode plot that is easier to be played for the control design purpose. But unfortunately, the Bode plot, they have only the mass interpretation of the gain margin, and you see crossover frequency, gain margin, phase margin, this kind of issues. Not as straightforward as the Nyquist stability, Nyquist plot. Okay, so you should be familiar with both plot. Okay, you should be very good to switch between the plot. Okay, so if anytime when you are not quite sure what happens, go back to check the Nyquist plot. Okay, so if you know what you want to do, come back to the Bode plot to do the design, to do the calculation, because this is going to be much easier in the Bode plot. So that is how you apply, how you can use these two plots appropriately. Okay? So you need to know both plots. That's the bottom line. Okay? So now, should we say the design of the control design? You know what? From this relation, I actually can reduce the control design, to a very simple words. Okay. So what do you mean by the control design? Okay. Once you know your closed loop system performance requirement, you know what? Sometimes I can even bypass the closed loop, system performance requirement. I'm not going to say what I want for the closed loop system. I straightforward saying that what I want for my open loop system. Okay, that's the same thing, right? Okay, for example, I'm going to say, okay, I want a control design such that the system, the open loop system has this much phase margin at this much specified crossover frequency. Okay, so the control design actually can be reduced to that if you can find a controller to achieve open loop system's phase margin at a specified crossover frequency. You see what I mean? Okay, you see the control design problem becomes the goal of the control design becomes this. Okay, as long as you can do this, then you achieve the corresponding closed loop performance requirement. No problem, right? Okay, so now next what I'm going to show you is the two design, is the phase lead and the phase lag compensator design. And we're going to see how we can manipulate the control, extra control, and such that the open loop system will achieve a desired phase margin at specified crossover frequency. You see what I mean? Okay. Okay. Now, yeah. Before I go for the to present the phase lead, phase lag, design, I want you to pay attention to this figure. Okay, because this figure it's a further details and that how you can get from the Bode plot for the tracking performance. How you can read from the Bode plot for the tracking performance. Okay, for example, if you have a type 0 system, and basically you can read the KP. Okay, in this case you have the KP, right? The position error constant. You can actually read the KP from the low frequency magnitude. Okay, because you see, if you have type 0 system, n equal to 0, okay, this is a type 0, n equal to 0 case, and if you can test it, your low frequency will be always flat. Okay, you will always start, the magnitude will always start from a flat magnitude. Okay, like this. You definitely will see this kind of flat line in the low frequency, very low frequency. Okay, starting. Okay, that magnitude actually can give you the information of the position error constant. Okay, how to read it? It's specified here. You see, it's specified here. Okay, now if you have a type 1 system, which means that n equal to 1. Okay, you have one integrator. If you do approximation of the Bode plot, you're gonna find out that you see the approximation is down here, right? You see, in the low frequency range, actually the magnitude is equal to this, k over j omega n. Okay, this is the base that how you can read this tracking performance error constants from the Bode plot. Okay, you see, n equal to 0, you have the flat because you have only gain k. N equal to 1, you have one integrator. So in the low frequency range, you definitely see a magnitude that is a downward line with a slope that is what? Negative 20 dB per decade. For sure. Definitely is like that. Because you see this one, and when n equal to 1, you have a j omega in the denominator. So in the low frequency range, it will definitely for sure showing a downward line with slope that is minus 20 dB per decade. So in this case, you extend that the low frequency magnitude, find out the crossover point with the 0 dB, then you can actually find out what is the velocity error constant from that. Okay, from this reading. Okay, see, this frequency actually just right equal to the error constant, velocity error constant. Okay, that will be straightforward. Okay, now when you have a type 2 system, and you're gonna see in the low frequency range, you're gonna see a downward line, but with a slope that is minus 40 dB per decade, right? Okay, so you see on n equal to 2, you have a j omega's square. So definitely you're gonna have this downward line with minus 40 dB per decade. So in this case, once again, you just need to find out the extension of this magnitude with the crossover, point with the 0 dB, and this corresponding frequency is going to be equal to the square root of the Ka, the acceleration error constant, right? Okay, so this is the way that you can read from the Bode plot. Okay, you cannot read it from the the Nyquist plot. Okay, so this is, you see, that this is a better way to use a Bode plot instead of a Nyquist plot. Okay, so that is something that you need to pay attention. Okay, you need to know. Well, if you do not go for this way, you can still find the Ka, Kp, and the Kv, right? You can still find out that. Okay, but it's just if you know how to read it from plot, you have one more approach to get this information. Okay, so it will give you the flexibility. Okay, sometimes it's easier to read it from the plot. Okay, so yeah, so we're gonna see what exactly it's gonna be the the control design. Okay, so before we go for the control design, you know what, I'm gonna show you that okay, this G of S actually it's a combination of the P and the C, right? Okay, and I've talked about this many times. What does this mean is that this is your plant model, which is your systems model, and this is the controller to be designed. Controller to be designed. Okay, and initially, your first step, it's always to evaluate the P of S when assume that the C of S is equal to 1. In other words, without the control, you're going to evaluate the open loop. You see, without the control action, your plan model is the open loop system transfer function, right? So you evaluate, when we say you evaluate the open loop system, that's just like that you evaluate the plan model itself. That makes sense because you need to identify what's going on with your system, right? Okay, if it is good, if it is bad, and if it is bad, what is bad? That's something you need to identify before you can go for the control design. If you don't know what is the deficiency of your plant, how can you what is the base for you to go for control design, right? Okay, so exactly the control design is that okay, if this guy does not satisfy my closed loop requirement, okay, you see here I'm using the relation between the open loop system and the closed loop performance, right? Okay, so when we evaluate that, we already know, we're gonna know what's the deficiency between the open loop using the plant itself to form a closed loop and the desired closed loop system, right? Okay, you're gonna identify the deficiency. Okay, and then if PS cannot achieve the satisfied closed loop performance, then what? Like what I said, because this is the plant, that normally you can't change the design of the plant. Okay, you're not the designer of the plant, all right? You're just the user of the plant. Okay, but it just, you find out that this guy does not work well. Okay, so what are we gonna do? If it does not satisfy your expectation, okay, the only thing you can do is to add extra C of S, the controller. Okay, that is, this C of S is in your hand. But what is gonna be the base for you to figure out this C of S, the controller? Yeah, you see, we do have the base. It's that we're gonna find out the C such that this control the open loop system, right? Control the open loop system, G of S. Okay, such that this is G of S, it's gonna show what I want. Okay, then that raises one question. So what is gonna be the ideal shape of this controlled open G of S? Idea. I'm talking about idea because I just want to know that not all the time you can achieve that, okay? Otherwise, we won't call it idea, okay, right? We just call it best. But unfortunately, this is just an idea system. This is just the wish list, okay? But in practice, we are not always can achieve this kind of idea, performance, okay? Okay, so, but still help you what constitute a good system, okay? So it is all characterized in this figure, okay? See, this is the Bode magnitude plot, okay? Let's see what an ideal open system will yield, okay? You see, if you look at that, this is the low frequency range. This is the phase margin crossover frequency, okay? Phase margin crossover frequency, okay? This is the high frequency. So this is the low frequency range. This is the phase margin crossover range. And here is the high frequency range, okay? So roughly, any system can be roughly classified into this 3 frequency range, okay? Okay, so in the low frequency range, what do we need? We need the magnitude to be high. Why? Because you see, this is because of the tracking, requirement, right? Remember, you see, the tracking, you see, Kp, if you find out the position error constant, then you know that the tracking with respect to unit step signal is equal to, the error is equal to 1 over 1 plus Kp, right? From that chart, okay? From this chart, right? See, we can find out that the tracking error will be equal to 1 over 1 plus Kp. In other words, the Kp, the higher the Kp, the smaller the error. So same thing for the, the Kv and the Ka, velocity error and the, acceleration error, right? Okay, so you can see that that will make the ideal systems that, okay, what do you exactly want in the low frequency range? Well, you want a higher Kp, Ka, Kv. That means that you need to make the low frequency range magnitude as high as possible, right? It makes sense, right? Okay. And so now you can understand why we need more integrator, okay? Because you know what? If you have one integrator, minus 20 dB per decade, the slope. If you have a 2 integrator, it will go to the, minus 40 dB per decade, right? Okay, which one has a higher magnitude? Apparently, if you have a double integrator, your magnitude could go, much higher, right? So now you can understand why you have 2 integrator. It will have better, tracking performance than the 1 integrator and the no integrator case, right? The type 0 and type 1. The higher the type, the better the tracking performance, right? Because you can track more signal, okay? Either perfectly, or if it is not perfect, you can reduce the error, okay? So there is no doubt about that. Okay, for the low frequency, we want this, magnitude to be as high as possible. Okay, now then let's move to the, the crossover frequency, range. Okay, now you see, unfortunately, if you have a steep, crossover here, you're gonna find out the system will not be stable. Okay, why? Because you see, we said that the slope here actually represents the order of the system showing up in this range. Okay, see, if you have any crossover that is more than 40 dB per decade, okay, at the crossover, okay, any crossover line around the, you know, this omega C range, okay, this is actually we use the omega PM, right? Okay, the phase margin, you know, crossover frequency. If you cross that with a slope that is more than minus 40 dB, you know what? You forget about it. Your system will not be stable. Okay, so if you figure out what does this mean is that if you figure out the controller and then evaluate the G of S, and you find out that here your crossover is what, more than steeper than the minus 40 dB per decade, you know, forget about it. Your system is, your closed-loop system will not be stable. Okay, your closed-loop system definitely will not be stable. So what you need here is a flat crossover. Okay, less than minus 40 dB. Because you know why? Because if the crossover is more than minus 40 dB, your system is gonna yield the phase, negative phase is what? Is more than minus 180 degree. You can draw the Nyquist plot for that case. The system, the encirclement around the system, around the minus 0 point in that case will happen. So the system will, closed-loop system will not be stable. You see what I mean? That's the reason. Okay, because in this case, you're gonna have a negative phase margin. Okay, you're gonna have a negative phase margin. Okay, you have too much negative phase. Okay, you have too much negative phase. Okay, but if the crossover, you know, slope it's less than minus 40 dB, then you know that your phase lag, the maximum is no more than minus 180 degree. Okay, which you could have reasonable phase margin. So that is why there is a good chance for the system to be stable. Okay, there's a good chance, okay, for the system to be stable. Okay, so this is one indication. So this is what we needed. Okay, what do we need? Okay, and now for the high frequency range, you see, let's say this is your bandwidth. I mean the bandwidth, you know, indication. Okay, because you're using omega m to indicate where the closed loop bandwidth is, right? So what does this mean is that in the high frequency range, which is above the bandwidth, you know what? You need the magnitude of the, you know, the open loop system to be what? To be roll off faster, as fast as you can. You can understand, because you see, if you have the magnitude of roll off, you know, faster, you know, steeper, you know, drop faster, this means that any frequency signal above this value, above this cutoff frequency, will be hard to pass through the system. Now, what exactly in this range? What exactly is going to be the nature of the signals in this range? Noise. Okay, so for noise rejection purpose, we want the high frequency range magnitude to be, you know, as low as possible. Okay, to be as low as possible. Okay, so it will, you know, attenuate the high frequency noise, you know, big time, right? So exactly this. Let me erase that to show you this desired, you know, open loop systems Bode plot. Again, I'm saying that this is the desired. Okay, I'm not saying that you can definitely achieve it. Okay, you know why? Because you see, you need a magnitude here is a steeper, because you want a higher magnitude, right? At the low frequency range. How can you guarantee that it becomes flat across the, you know, the phase margin crossover frequency? Okay, these two requirements, they are inherently conflicting. Okay, they are inherently conflicting. You got to be careful to play with that. Okay, it's not gonna be like you see, if you say, oh yeah, I can raise the magnitude at any place that I want, and also I can, you know, make it flat at the place that I wanted it to be flat. You know what? That's like a free lunch. Okay, that's like a free lunch. It's not easy to make it happen. Okay, in practice, normally it is hard. Okay, so that is why you need actually sometimes you need to do the trade-off. Okay, you need to do the trade-off. You need to sacrifice the tracking performance a little bit and to accommodate to the crossover requirement, because a crossover requirement is definitely more critical, right? Okay, see, if you don't have the desired crossover frequency slope, your system becomes unstable. Okay, if the system is unstable, you see, if you, let's say if you have a crossover here, the system, closed loop system becomes unstable. you do you still want to tell me that how high the low frequency magnitude is going to be? It doesn't make any sense, right? Because the closed loop system becomes unstable. Your high magnitude in low frequency does not make any sense. Okay, okay. So that is why in practice we need to do trade-off here. Okay, it's not always that you can achieve this ideal Bode plot shape for the open loop system. Okay. So now we can talk about the design of the lead lag compensators. Okay. Now the design, it is like what I said. The purpose, if we use one sentence statement to describe what exactly is the lead lag compensator design, and this is it. Okay, this is just when we say lead lag design, we mean that we use the lead lag factor C of S to manipulate the stability margin and the 0 dB crossover frequency, which is the phase margin. Phase margin, this is exactly the omega PL. Okay, 0 dB crossover frequency, that is equivalent to say that the phase margin crossover frequency. Okay, so they're the same, right? Based on this figure we talked about before, right? Okay, so now, yeah, then first question is that what constitute the phase lead and the phase lag compensator? Well, this comes from the definition that we talked about before, right? So when you have a transfer function, we define the phase lag and lead and lag transfer function. If you remember that, we use the transfer function's phase, if it is a positive, if it is a negative, to define it is a lead factor or lag factor, right? See, specifically, if this transfer function of the controller yields a positive phase, we call it a phase lead compensator. And if you have a negative phase, we call it a phase lag compensator. And don't forget it, on the Nyquist plot, we have a very clear indication of what a phase lead and a phase lag compensator means for the Nyquist plot, right? You see, let's say if this is the Nyquist plot of G of S, of this one, of this guy, okay? And then you add a phase lead compensator. Can you tell me, just tell me, in terms of the phase purpose, where this plot is going to go? Use simple words to tell me. Someone, can you perceive that? You see, let's say if this plot is the plot of G of S, now you apply a C of S that is the phase lead compensator with a positive phase. Can you tell me how you're going to predict this plot is going to go? Because we are talking about the CS G of S plot, right? After you apply the C of S, the controller, then you plot, actually we're talking about this guy's plot, okay? That's still open loop, right? Okay, can someone tell me, can you predict where the plot is going to go, roughly, in terms of phase? Someone? Come on. Come on, quickly. Someone. You know what? If you don't volunteer. Don't do voluntarily. I will name it. Okay, I will call the name. Okay. Yeah. Okay. Yeah, that is good, Samantha. Yeah, and no budget. Okay. Yeah. It simply to say you're gonna predict that the plot is gonna rotate counterclockwise, right? Because you add a positive phase. At a positive phase, this is a negative phase. Remember, this means the phase is negative, right? So you add a positive phase, then you're gonna drag this plot, counterclockwise. Okay, when you drag counterclockwise the plot, what happens to the alpha? Phase margin becomes larger, right? See, from the Nyquist